This video is about displacement, velocity, and acceleration in simple harmonic motion. We'll look at these concepts exactly in this order. First displacement, then velocity, and finally acceleration. Let's begin with displacement. In subtopic 4.1, we learned how to graph simple harmonic motion. If you would like to revise these concepts, feel free to go back and watch some of the videos from subtopic 4.1. One of the things we learned was that the displacement time graph for the motion of an object that performs SHM, or simple harmonic motion, is either a sine or a cosine graph. In topic 4, we learned how to sketch and read these graphs, but we did not describe the motion using an equation. Since graphs can be described by equations, the motion of the object performing simple harmonic motion can also be described by using equations. We will learn some of these equations in this video. Let's start with the displacement equation. These are the two formulae that you find in the IB Physics data booklet, and here are the variables. Using this equation, we can find the displacement of the object at any given point in time during its motion. Let's see an example to further explore these equations. Here is the displacement time graph for a particle that oscillates with simple harmonic motion. To create the equation for the displacement in terms of time, we have to find the maximum displacement and the angular frequency of the object. The maximum displacement is equal to the amplitude of the graph. It is 3 centimeters. So for x0, we get 3 centimeters or 0.03 meters. We learned in the previous video that angular frequency, omega, is equal to 2 pi divided by the time period. We can see from the graph that it takes the particle 4 seconds to complete one full oscillation. Therefore, omega is equal to 2 pi over 4, and this is 0.5 pi radians per second. Now that we have x0 and omega, the next question is which of the two formulae to use. Do we have a sine graph or a cosine graph? Of course, the graph we see here can be described by a sine or a cosine equation, but since the formulae in the IB Physics data booklet do not include a horizontal translation, in other words, nothing is added to or subtracted from t, the graph we see here can be described by using the sine equation. Don't worry if this reasoning wasn't entirely clear. An easy way to decide in this context whether the graph is a sine graph or a cosine graph is to see whether the graph starts at 0 or at one of its maximum displacement positions. When a graph starts at 0, it is a sine graph, and when it starts at one of the maximum displacement positions, it is a cosine graph. The graph we have in our example here starts at 0, which means that it is a sine graph. Therefore, its equation is x is equal to 0.03 times sine 0.5 pi t. We could use 3 instead of 0.03. In that case, we would just have to keep in mind that the displacement value we get is in centimeters. The fact that the graph starts at 0 also shows us where the particle is when we start observing it. When x is equal to 0 on this graph, it means that the particle is at its equilibrium position. Therefore, when we start observing the particle, it is passing through its equilibrium position. Since after this the graph increases, we can also conclude that the particle is moving in the positive direction. Next, let's see what happens when we start observing the particle at a different position, for instance, at one of its maximum displacement positions. In such a situation, the graph looks like this. Since we are observing the exact same motion as before, the maximum displacement and the angular frequency are exactly the same. The only difference is that here we start observing the particle when it is at the positive maximum displacement position. Therefore here we will use the cosine equation to describe the motion, and we get that x is equal to 0.03 cosine 0.5 pi times t. Now that we learned about the displacement equations, we are ready to move on to velocity. We learned in subtopic 2.1 that the gradient of a displacement time graph represents velocity. For the next minute or so, we'll go into a mathematical explanation of how the velocity equations can be derived from the displacement equations. It is not absolutely necessary to know the details of this mathematics for your IB physics course, so don't worry if you get a bit lost here. You will still be able to use the equations when solving problems. You have either learned or will learn in your math course that the derivative of a function shows us the gradient of the graph. Connecting this with the point above, we can conclude that the derivative of the displacement time equation is the velocity time equation. Here are the two displacement equations that we just learned. In the IB Physics data booklet, you will also find two velocity equations. So when we take the first displacement equation and differentiate it, we get the first velocity equation. The derivative of sine is cosine, and omega appears in front of x0 because we are using the chain rule. The inside function in the chain rule is omega t, and the derivative of omega t with respect to t is omega. Similarly, when we differentiate the second displacement formula, we get the second velocity formula. The derivative of cosine is negative sine, and again we are using the chain rule to get the omega at the front. Here are the variables that are present in the velocity equations. These equations allow us to calculate the velocity at a certain moment in time. In some cases, it might also be useful to calculate the velocity at different points during the particles or the object's oscillations. There is a formula in the IB Physics data booklet that will help you do this. Here is the formula, and these are the variables. You see a plus-minus sign in front of the omega in the equation. Depending on the problem that you're solving, you will choose either the positive or the negative sign in your final answer. To make the correct choice, you will need to analyze the given situation, which can include the graph or graphs given in the question, and then decide whether the velocity in the given position is positive or negative. Now that we have learned the velocity equations, we are ready to move on to acceleration. A few minutes ago, we saw the relationship between a displacement time and the velocity time graph. Similarly, there is a relationship between the velocity time and the acceleration time graphs. Recall from subtopic 2.1 that the gradient of a velocity time graph represents acceleration. Connecting this with the idea that the derivative of a function shows us the gradient of the graph, we can conclude that the derivative of the velocity time equation is the acceleration time equation. These are the two velocity equations that we just learned, and I will also include the displacement equations from an earlier part of the video, because we will also use these to derive the acceleration equation. So to find the acceleration equation, let's start by differentiating the first velocity equation. The derivative with respect to t, so dv dt, or in other words, the acceleration, is equal to negative omega squared times x0 times sine omega t. We get this because the derivative of cosine is negative sine, and we are also applying the chain rule and multiplying the entire expression by the derivative of omega t. This is one way to express the acceleration time equation for simple harmonic motion. Working a bit further and simplifying, we can write this equation in a different form. You might have noticed that the expression x0 times sine omega t is the same as the expression in one of the displacement equations. Therefore, we can replace it by the displacement, so x. This gives us that a is equal to negative omega squared times x. Let's see if we arrive to the same result by differentiating the other velocity equation. So dv dt is equal to the acceleration, and this is equal to negative omega squared times x0 multiplied by cosine omega t. This is another way to express the acceleration time equation, and this equation can also be further simplified. x0 times cosine omega t is the other expression for the displacement, so substituting this by x, we get that a is equal to negative omega squared times x, which is exactly the same as we found in our previous working. This formula for acceleration is included in the IB Physics data booklet, and as a reminder, here are the variables that are present in this formula. Recall from subtopic 4.1 that one of the defining features of simple harmonic motion is that acceleration is proportional to the displacement from a fixed position, called the equilibrium position, and then the acceleration is always pointing towards the equilibrium position. Mathematically, we can express this as a is proportional to negative x, or a is equal to negative kx, where k is a constant. If you compare the equation that we learned in subtopic 4.1, so a is equal to negative kx, with the equation that we derived here, so a is equal to negative omega squared times x, you can see that the only difference is that in one equation we have k and in the other we have omega squared. We said that k is a constant, and if you think about it, omega squared is also a constant because angular frequency does not change. Therefore we say that the equation a is equal to negative omega squared times x is the defining equation of simple harmonic motion. Let's summarize what we have learned in this video. Our main goal in this video was to derive the displacement, the velocity, and the acceleration equations of simple harmonic motion. We used differential calculus to do this. Two important reminders here. The first is that you don't have to know or memorize how to derive these equations. The second is that even though understanding differential calculus can help you understand some concepts better in physics, in the IB Physics course you're not expected to know differential calculus, and it is possible to solve all exam questions without using calculus. So let's see the equations that we derived in this video. We learned two equations for displacement, along with the variables, three equations for velocity, two of which are for velocity time, and one of which is for velocity displacement, and we finished up with one acceleration equation. To conclude, we added that a equals to omega squared times x is called the defining equation of simple harmonic motion. This completes our discussion of displacement, velocity, and acceleration in simple harmonic motion. In the next video, we'll learn about the simple pendulum.